Imagine a fortress, not one with tall stone walls and a moat, but one buried deep beneath the earth. A command center, a weapons depot, a secret lab, all shielded by dozens of feet of solid rock and reinforced concrete. You can see the entrance on a satellite photo, a tiny dot on the landscape, but the real prize, the critical target, is hidden far below. How in the world do you reach something like that? You can't just drop a regular bomb on the surface. That would barely scratch it, like throwing a water balloon at a sidewalk. It would create a crater, sure, but the important stuff underground would be completely untouched, safe and sound. This is one of the biggest challenges in modern military strategy. It's a classic problem of access. For every measure, there is a countermeasure. Humans have been building fortifications for thousands of years, and for just as long, other humans have been figuring out how to get through them. But digging in, going deep underground, is the ultimate defense. It uses the planet itself as a shield. So engineers and physicists were faced with a monumental question: how do you deliver an explosive payload to a place that is, by design, unreachable? So what exactly is a deep penetration bomb? Let's get our definitions straight. A standard aerial bomb, like the kind you see in old war movies, is basically a thin-skinned container full of explosives. Its job is to detonate on impact or just above the ground, spreading shrapnel and blast pressure over a wide area. They're great for taking out buildings, runways, troop formations on the surface, but against a hardened, buried target they are almost completely useless. The vast majority of their energy would dissipate into the air and the topsoil. A bunker buster, on the other hand, is built completely differently. It's designed with one primary goal in mind: penetration. To achieve this, it has to be incredibly strong. Instead of a thin metal shell, its casing is made from a super-hardened, high-strength steel alloy. We're talking about a casing that can be inches thick. This isn't just a container for explosives, the casing itself is a weapon. It's the tip of the spear. This robust construction is absolutely vital because the bomb needs to remain intact as it smashes through layer after layer of incredibly resistant material. The second key difference is what's inside and how it's used. A bunker buster carries a powerful explosive charge, but it's paired with a delayed action fuse. This is the brains of the operation. The fuse can be programmed to detonate not on impact, but a fraction of a second after impact, giving the bomb the crucial window to travel deep underground. Let's break down the science. It's awesome. The core principle at play here is kinetic energy. The formula for kinetic energy is 1/2 times mass times velocity squared. Mass velocity squared, v squared. This little equation tells you everything you need to know about why bunker busters work. Notice that velocity is squared. This means that speed is a huge factor. Doubling the mass of the bomb doubles its kinetic energy, but doubling its speed quadruples its kinetic energy. This is why these bombs are dropped from high altitudes, allowing them to accelerate under gravity for a long time, reaching speeds of over 1,000 miles per hour, faster than the speed of sound. When the bomb hits the ground, all of that incredible kinetic energy has to go somewhere. This is where Newton's laws of motion come into play. An object in motion stays in motion. The bomb wants to keep going. The ground, rock, and concrete want to stop it. The bomb's immense momentum allows it to win this battle, overpowering the resistive forces and carving a path downward. Think of it this way. Try to push a screwdriver through a block of wood with just your hand. You can't do it. Now hit the back of the screwdriver with a hammer. It sinks right in. The bomb is both the screwdriver and the hammer's force combined. Its mass is the hammer, its hardened nose is the screwdriver, and the high-altitude drop is the swing. Now let's get into the nitty-gritty of the build. You can't just take any old bomb, make it heavy, and expect it to burrow. The materials science and aerodynamics are just as important as the raw physics. First, let's talk about the shape. Bunker busters are long and slender like a giant dart. This is not an accident. This shape, known as a high sectional density design, concentrates the entire mass behind a very small, narrow point. This maximizes the pressure at the tip, just like how the tiny point of a needle allows it to easily pierce fabric. This dart-like shape also makes the bomb aerodynamically stable when dropped from 30,000 feet. Fins at the back provide stability, ensuring it hits nose first at the perfect angle. Any deviation would cause the bomb to hit sideways, wasting all that kinetic energy. The casing material involves serious material science, advanced steel alloys mixed with nickel and chromium. These alloys are heat-treated and forged to create material that is both exceptionally hard and incredibly tough. Hardness prevents deformation on impact, while toughness prevents shattering under shock and stress. It's a delicate balance. Inside, the explosive payload is specially designed to be insensitive enough not to accidentally detonate from impact violence. The delayed action fuse provides the specific signal needed for controlled detonation after penetration. This technology has been key in military arsenals for decades. The concept took off during the Cold War, when the United States and Soviet Union built deeply buried command bunkers to protect leadership. But the first major public demonstration came during the Gulf War in 1991. The Iraqi regime had constructed hardened aircraft shelters and command bunkers, many built by European contractors. Conventional bombs were proving ineffective. This is where the GBU-28, nicknamed Deep Throat, came in. Legend says early prototypes were rapidly built using repurposed 8-inch artillery barrels for casings. In the final days of the war, two 5,000-pound laser-guided bombs struck the Al-Taji bunker complex. Post-strike analysis showed they punched through over 100 feet of earth and concrete before destroying the facility from within. Since then, bunker busters evolved. The Massive Ordnance Penetrator, MOP, GBU-57, the modern monster. A colossal 30,000-pound bomb, carried by stealth bombers like the B-2, designed to defeat the most deeply buried targets such as alleged underground nuclear facilities in Iran and North Korea. Weapons like the MOP serve as deterrents. No matter how deep you dig, you cannot hide. These applications show the strategic importance and how they've changed modern warfare dynamics. Fortifications once considered impregnable are now vulnerable, removing sanctuary status and creating a continuous arms race that burrows further underground. As with any powerful technology, deep penetration bombs come with serious ethical and safety considerations. On one hand, they are seen as more precise, targeting specific military bunkers to avoid widespread surface destruction. In theory, this could reduce civilian casualties by focusing destructive power exactly where intended. The goal is to surgically remove a critical node without leveling the surrounding area. However, the reality is more complicated. Precision is relative. The bomb may hit its GPS coordinate accurately, but targets are often near civilian areas. Destroying a deep bunker creates a massive underground explosion with unpredictable surface effects. It can cause localized earthquakes, collapse nearby buildings, and destroy underground infrastructure. The line between surgical strikes and collateral damage can get very blurry. There's also the question of what's inside those bunkers. Striking a facility believed to hold chemical or biological agents could release them into the environment. This puts enormous burden on intelligence agencies to be absolutely certain, a task made difficult because targets are hidden and secret, and that's the big picture. Deep penetration bombs counter the technology of hiding. For every action there is an equal and opposite reaction. Could weapons strike miles beneath the surface? The science says yes, but the real question is, should we?